Obviously, that wasn't anything.
All right. Thank you, everybody, for joining us for our final honors program colloquium of the spring 2024 season. That's crazy. But we are very happy to welcome Dr. Greg Hogan, Associate Professor of Chemistry and incoming Division Chair of Natural Sciences and Mathematics here at A&M Texarkana. Very exciting. We're running a little late, so we're just going to jump right in, and he's going to be talking to us today on investigating selective guest inclusion within 2D and 3D metal organic frameworks. Dr. Hogan, take it away, sir.
Thank you. You want to, I guess we'll pop it into
You may do whatever you like.
screen mode.
Oh,
No, I guess.
oh dear. There it is. Okay, it's all right. It all works.
Okay, so trying to figure out which direction I want to stand on with this.
However you want to do it, sir.
So it looks like they are seeing this green, red thing, orange.
Yeah, I'll get rid of that.
It just says turn on.
Mhm.
Turn it on. Okay.
Sure. Don't know what that means, but okay.
Okay. Got it.
You forget how terrible Microsoft is at everything. Okay.
Okay. I think we
Oh,
got
and it is recording me saying, oh, how you forget how terrible Microsoft is. at everything.
All right. So thank you. Sorry for the delay. Like I mentioned a wee bit ago, I thought this was Thursday, so I was actually working in the lab trying to collect more data for this talk and for also a talk that myself and two students are going to travel to Denver this summer to deliver at the American Crystallographic Association. So as you've been told by Dr. Nakashian, we're going to look at investigating selective guest inclusion, but we're going to focus only on 2D because the 3D just hasn't been working for us since forever. So, and you'll see why just shortly, a brief little snippet into it, but we just weren't successful in crystallizing. How do I move?
You might have to do it here on the slide. Obnoxious. There we go.
What did you do?
I just hit the mouse button because it's sitting on the forward. Yep.
This
I'll
one?
move to the next one to do that.
That?
Yeah, sure.
Okay, I'll just make sure I got it.
I believe it would be this one here, if you want to
Okay.
advance the slide.
Okay, thank you.
We are professionals, sir.
All right, so the basic idea with us, we're generating hydrogen bonded metal organic frameworks. So the idea is that we're generating layered material. Layered material can be just standard, what we commonly see as things like clays, clay materials. Some of the basic examples, as you can see, is this silicate layer, which is a classic aluminum silicate of actual clay itself, a sodium montmorillonite. So as you can see, it has the two distinct features, a hydrophilic interlayer. So again, I'm sorry, I said, yeah, hydrophilic. So it is a water-loving interlayer. So in between its layers, it's going to love things like water, anything that can be soluble or will dissolve in water will fit perfectly and will encapsulate in between the what are going to be called the supposed to be hydrophobic layers, where now we have metal oxides that really do not dissolve in water. They're not water loving whatsoever. But the idea is that we generate layered structures and we're going to place molecules inside of it, because the biggest thing that we are looking for is that right little guy at the bottom, the ability for our frameworks to swell. Swell meaning for the actual interlayer distance to fluctuate depending on molecules that we place inside of our frameworks. And why do we study these? Well, now the list has grown since the last time I gave this talk. Some of the best ideas is that they become as sensors, so that in case of inclusion of a guest molecule, we can actually have some that are photoluminescence with its sensor ability. So if we put a certain molecule in, give it enough wavelength of light, if the correct molecules in our framework, we will see the light given off, kind of like a glow stick in essence. Storage, which is one of the biggest topics it has for its ability, is because it's an interlayer space. That interlayer region loves molecules. And so some of the biggest topics of concern right now is a lot of gas storage. the hydrogen economy. If we have mechanisms to store flammable gases in a more non-quote quote flammable toxic manner, i.e., we have a winner. Separations. This is actually something I was about to start collaborating with a gentleman from Oklahoma, that some of my frameworks, because of the molecules that it enjoys to include within its framework, works perfectly for DNA purification and separations. So a lot of DNA purification, DNA synthesis involves specific organic molecules, and some of the organic molecules are present in the picture that's on the screen. So it will work perfectly to purify extra molecules that were used inside of the synthesis for DNA. And last but not least, we have the possibility of being a catalyst. Is the one key feature that an inorganic chemist can always say that their materials is useful for. Metals are always a catalyst, especially transitional metals. So I'm not thinking of group 1 or group 2 metals, but the D block. Okay, so we have the possibility of a catalyst species, because in this framework here, we have a copper molecule right into the center of our metal organic framework, which is the guy right at the very top, middle, and at the very bottom. All right, so how do we investigate? Hey, there's Chuck. How do we investigate these materials? So, i.e., these are the fancy instruments that we get to use that we don't have the money for. At least now we've added one to this list that we do have. So all of our fancy instruments, number one, my research is all through crystallography. So number one is what is called X-ray analysis. And there's two types: single crystal X-ray diffraction and powder X-ray diffraction. Hoping during the summertime, we will have one be ordered and sending to campus, which is about $100,000 instrument. Single crystal X-ray diffraction, these I submit off to College Station because the instrumentation is just too costly for us. And this is actually where the bulk of our data comes from, is growing crystals and analyzing them through X-ray analysis. Number two, which comes in very handy, is the thermal analysis. And we just installed 2 weeks ago 2A, which is the thermogravimetric analyzer, and TGA, which is what I was actually running right before coming here. And hopefully it stops. So the good news with that one is that it actually will give us thermal data in the sense of we can look at weight loss, or we can also have for the second instrument, the differential scanning calorimetry, we can look at heat exchange within our frameworks. So we can either determine how much mass is being lost over a course of a temperature range, or we can look at the enthalpic relationships, or how much energy is being produced and giving off within our sample. 3, 4, and 5 are just some standard organic techniques, NMR, IR, and GCMS, that typically goes into play whenever we're just either we're making some basic analysis, or in my case, we do synthesis to form and create some of the molecules that I can't purchase. So always very handy. All right, so there's just to show you some ideas of what we do. Like I said, we grow crystals because everything's through X-ray diffraction. So you see the top two pictures are some oldies but goodies, some copper complexes. The three down at the bottom are more recent ones. The bottom left is a zinc complex. So as you can see, a fairly colorless crystal, but there is still some kind of slight orange hue into the actual solution itself. But zinc compounds typically crystallize off as a colorless species. The one in the middle, which is a beautiful looking little guy, reminds you of some nice ice crystals around Christmas time. That's actually a nickel complex, because you can see the light green hue into the actual crystals. And the other guy into the forehand is another copper complex, but different from the two guys on top. Okay. All right, so I always put this out because again, if I wouldn't have this, collaboration, there'd be no way in heck we would ever get what we're doing. Okay, is the fact that I invoke everything through crystallography. We saw the crystals. So we grow crystals and they get placed on this instrumentation that we can shine X-rays. And then with the X-rays, we can see the scattering patterns of all of the electrons, the electron density associated with each atom that's present. So anytime you see these wonderful pictures, right, these are pictures that are given and generated from X-ray analysis. So the picture to the left is what's called a modeled species. So more we're talking about the actual counterion. So that's the little small molecule to the right of the large one for those that can't see on that's on Zoom. Okay, so the modeled, and as you can see what happens, this is what's called a disordered onto the right-hand side. So what's happening is because of just standard entropic effects within all molecules, molecules move, right? They're free-floating movement within our frameworks. And so when we shine and bombard with X-rays, right? So what we're doing is seeing about 3 different picture patterns of the orientation of that disordered molecule. Okay, so that's where my crystallographer has to come in and set some key restraints onto that one counterion and allow himself to solve completely the entire molecule of what you see on the left-hand side. So huge thanks to, his name is Dr. Joseph Rabinskis over at Texas A&M in College Station. Without him, this work is not possible. Okay, so getting to the beginning of our, what I like to call, because if you do some data search off of Google Scholar or anywhere that you like to do your searches from, this area of chemistry is pretty newish. I'd say newish because again, it's probably from about the 80s, give or take. 2 original scientists by the name of Kitagawa and Omar Yagi developed these things called MOFs. So at the very top, you see I have what are called HMOFs. So MOF just stands for metal organic framework. So I investigate hydrogen bonded metal organic frameworks. So unlike what previous material has looked into, their metal organic frameworks are completely connected by coordinate covalent bonding. Okay, so it's the sharing of electrons through a metal center and an organic species, and we have the continuous array in 3 dimensions of this exact same chemical interaction. The difference where I come in is we use hydrogen bonding to associate and connect our framework together. So we have here a basic metal dicarboxylic acid. In this case, it is a nickel-based. So we're looking at the molecule on the top left-hand side. So it has 2 carboxylic acid groups in the peripheral edges of our molecule. And we're going to interact it with what's called an amine, 2 equivalents. So we're going to give 1 amine for each carboxylic acid. So 1 NH2 is going to interact with this OH species. All right, we allow it to sit after they have interacted together. And this is where, if I would have had my time, I was going to show a nice little video. The synthesis of this kind of reaction is one of the coolest things. Charles might be able to contest if he wants to, or attest to it. These metal organic species, when we place it in methanol water, it's a suspended solution. So it's a powder that's being mixed, and so it just looks like a cloudy substance. We add the amine molecule, a couple drops, solution goes clear. Okay, not colorless, because again, depending on what metal we have, but now we went from a cloudy solution now to a clear solution. so that all of those solid particulates have now interacted with the amine and have formed this charge-assisted hydrogen bonded species. So we technically have an inorganic salt, okay, in the grand scheme of things. Okay, the reason we look at this, it's because it's simple. The synthesis is simple, and our frameworks are stable. Okay, we claim stability because we'll see later in some data that we have frameworks that exist up to 200 degrees Celsius. Yeah, we can classify that level of stability. Okay, thermal stability. All right, and so that then allows us to now work on and focus specifically on our transport, the guest inclusion. Okay, so here are some of our beginning work that we've done here. So this is just to show you the basic synthetic approach that if we take a copper sulfate salt, we react it with what's called pyridine 2,4-dicarboxylic acid. So we just read the chemical reaction left to right. In a basic methanol water solvent system, this copper complex that we will just simply call copper PDCA, short for copper pyridine dicarboxylic acid. Right, again, another wonderful synthesis approach that we can just simply see everything that's happening. Copper sulfate dissolves very easily in water. Pyridine dicarboxylic acid dissolves very well in a very high high amount of solvent methanol water, but both solutions dissolve. You mix them together, let it mix for at least for good 5-10 minutes. And then you start to see a precipitation of the copper PDCA come right out of solution. So we're allowed to filter it based on just basic gravimetric filtration. Okay, so simple, easy techniques. And that's the key. Okay, and so here's just a selfless, little plug of our research. So this is one of our publications from the Journal of Molecular Structure, where we have underwent the inclusion of some alcohol molecules within our copper framework. And so that's going to be the data that we are going to show you. There's what I have circled. Those are 2 undergraduate students. So the one thing I'm always proud of is that the undergrads, they get their hands dirty, they get in here, they create these frameworks, and they get recognized with publications, which I was hoping that data would come back to Mr. Charles in the room, that he's going to be on a publication. Hopefully that will come out hopefully in the fall, should be submitted over the summertime. Okay, so how do we make frameworks? Frameworks are developed very simply. We take the copper PDCA, we react it again with the 2 equivalents of our, of our amine molecule. Go ahead. Excuse me. 2 equivalents of the amine molecule in, again, a methanol water mixture. And typically we like to give a second molecule that we often will try to include inside of our framework. This is going to be our guest molecule. In this case, we chose bromobenzene. And the idea with bromobenzene was I already thought that this molecule is going to be too large to fit inside, because what we do like to start off with is get a basic framework. Okay, so and as you can see, here's our crystal structure that was generated. Right, doesn't look like much, but once I pop it into my X-ray software that I have, what's called Mercury, I can expand my unit cell of my copper complex that was just shown. We can expand it into 3 dimensions. In this case, we'll just focus on 2 because everything is still going back through the board in the exact same orientation. So as we can see, we have a nice layered framework. And in the very center, you can see kind of where 2 of the layers kind of butt ends with one another. So in the framework systems, this is what's called an ABA layer, because that's the repeating pattern. A is the top layer, B is the interlayer, and then again, we identified again another A. So the repeating pattern is an ABA, because again, what happens? ABA. So ABA frameworks are often known as a bilayer species. So we have this bilayer interregion where we do have water molecules that are kind of hanging out inside of the bilayer. Okay, what's interesting also is typically what we have seen in the past with all of our metal frameworks is that they often incorporate into an octahedral geometry, but here we do not have an octahedral geometry. Our molecule is 5-coordinate into a square pyramidal, and the reason more than likely is this water molecule is quite labile, so it likes to come off freely because of the low threshold of energy, and it just incorporates itself into the bilayer. Every structure that we have generated with a no included guest molecule always exhibits this exact same structure. Okay, so consistency. All right, so same thing. Next framework, same kind of same setup, but now we're gonna layer with 2-octanol instead of bromobenzene. Okay, we chose a whole gambit of different types of guest molecules, and we're just going to show you a couple here. So 2-octanol as our guest molecule, and voila. Looks a little different, but quite similar. So we do still see the ABA repeating bilayer structure, ABA, and then again it repeats, which is wonderful. 2 noticeable differences. Okay, the first one is inside of the bilayer, we no longer have the water molecules. They have disappeared. Not really. They have just migrated to a different location. So to help incorporate guest inclusion, those water molecules that were inside of the bilayer are now expanding the actual hydrogen bonded layer. Okay, and we should also be able to identify, only on a select few of these I'll circle out, right? We have guest inclusion. Okay, so I just spaced them out. So as you can see, we technically will have 3 guest molecules, the 2-octanol, that is onto the top framework. I left one out in the center. And then on the bottom framework, again, we still have the repeating 3. And I only chose just simply to circle the bottom, the middle one. Right, but again, we still see the same type of disorder like we've seen earlier, because as you can see within either of the circled guest molecules, the oxygen atom of the hydroxyl group is the one that's in red. And what do we see? A red on either side of the molecule. So what's happening is we have the octanol pretty much facing into the left direction where the hydroxyl is pointed down. And if we take it, flip it, rotate it, then now it's pointing up onto the top-hand side. Okay, so we can't get complete and remove all disorder aspects, but we do know that the octanol molecule was included because, again, we see the correlation, the weight percentage and everything that we will increase our total mass by is pretty much in agreement with all of our experimental data. And this is one of them here. This is a shot from what is the thermal analysis. This is the TGA. Okay, so what we identify within our thermal analysis is, again, we see that our mass percentages started way at the very top. So we have all mass. And then as we heat, in this case, we're going up to about 450 degrees Celsius, we can see where we have small weight losses. Okay, so the green line is simply just the weight percentage versus temperature. And the blue line is what is known as, it's the derivative of our weight check, of our weight loss. So now we're investigating and apply a first derivative to our green plot. So we're looking at how the change of mass loss is occurring, because these derivative plots helps us to get a better analysis of the weight loss itself. So when we want to choose a good region to measure the exact weight loss, well, we go to the derivative plot and we find where right before we get the huge increase and down for our decrease, those are the regions that we look for. Okay, so we get good correlation because as you can see in the very first one, we're probably picking up nearly about 10 to 12% weight loss very early, which is again a good correlation and indication of our octanol molecule. Okay, now again, another plug. So looking also with our copper species, we also can include pyridine-based molecules. Okay, and again, we have another student, undergrad researcher, that's Hong Nguyen, gentleman who graduated just a few years ago. Now, there we go. And so a similar process. We have our copper PDCA plus the alpha benzylmethylamine, and we generate our crystal structure. In this case, we have now given and fed it 4-methylpyridine, also known as 4-picoline. Now, gotta remember the button. So look at it. We grow it in our 2 dimensions. Framework looks pretty similar to what we've seen with the octanol molecule. We still have our ABA layer, so I put an extra A on top. I don't know why, but we still have ABA, and so we have our repeating bilayer framework. Again, no water molecules encapsulated inside of the bilayer. Water molecules are in between, expanding the hydrogen bonded framework. Okay. And what else do we see that didn't show up? Now I got to figure out how to go back without Craig. Nope, dang it. There we go. So I didn't circle, I just put a box. So again, we have a non-coordinative guest inclusion or guest insertion because right here into the center, do we have a mouse? No mouse cursor. All right, so right into the center, as you can see, this blue, kind of this little blue area, the blue atom, that's a nitrogen from pyridine. And so what we have kind of a directionality of our pyridine molecule, that the lone pair of our pyridine is pointing out through our board on the first one, and then its neighboring is pointing back. And so we'll see that continuous repeating pattern for our 4-methylpyridine molecule. Okay, so we can include these molecules. All right, we see it, it continues. Trying to stall while I get the thing to move. Come on, guy. Okay, we'll go that way. So one of the last ones that we'll have. So same framework. Now we're going to look into the use of 4-T-butylpyridine. So we're going to expand and increase the size of the substituent onto the pyridine molecule, keeping the 4 position, because what we have noticed with almost all of our included frameworks is that anything onto an aromatic molecule, if it's on the ortho or meta position, so the 2 or the 3 position, we're not seeing complete guest inclusion. The longer, straighter, the better. Okay, so that's why we look at 4-T-butylpyridine, expand the size of our framework, or of our guest molecule inside the framework, to see, do we have enough space? All right, now, looks a little bit different. Okay, instead of being a complete horizontal framework, we have kind of a slight decreasing slope, right? So it's kind of a framework that's kind of tilted in essence. But framework is still the same. It's an ABA bilayer. Again, 0 water molecules inside of the bilayer. Water molecules are again still assisting with the actual framework within the hydrogen bonded framework. But now what happens to the T-butylpyridine molecule? it's now coordinated to the metal center. Because you got to remember, originally we stated that this copper complex was a 5-coordinate species, and it still is. So we simply just did a ligand substitution of the one water molecule that was present onto our copper, and we have now substituted the T-butylpyridine. More than likely, the basicity of T-butylpyridine, it was large enough that we were able to undergo a standard ligand substitution. So similar to like an SN2 kind of a reaction in organic chemistry, but with the metal species instead. Okay, so ligand now has coordinated to our metal, so it still technically is a guest inclusion, but now the inclusion became a coordinated inclusion. Okay, so here's just some other things that we're working on in our lab to assist us to help continue our projects into the 2D and 3-dimensional selective inclusion. We also have to do synthesis. Because like I said, some of our molecules, we just cannot purchase because, heck, some of the chemical companies just don't know what I really want. So here, if we take 4-aminopyridine plus 4-nitrobenzoyl chloride, so it's an acid chloride, very highly reactive species, apply it with some triethylamine in a DCM dichloromethane solvent system, we can undergo a nice collaceous condensation reaction where what we have done is combined the amine molecule to the acid chloride and formed and tethered our molecules together. So that now we have this extended nitro molecule, which is not bad because it's close. Everything we've been looking at has been amine molecules, but nitros aren't that bad, right? NO2, pretty close to NH2, because all we have to do now is to do a standard reduction reaction. In this case, I found this one. I always love the interesting reaction. So as you can see, there's our nitro group. In this case, if we use activated palladium on carbon with a little hydrazine in a methanol solvent, we actually can undergo a hydrogenation of our molecule. And because now you see in our crystal structure, remember, oxygens are red. Now we have the NH2, the hydrogens are our white spheres. So we actually have undergone the reduction of our molecule. But the only problem I've had with this project, and I've tried a few different directions, is that we generate a pyridinium chloride. So now our pyridine molecule is positively charged. It picked up a proton, and we have a counterion chloride that's free and dissociated. So always a drawback on everything. So we've kind of pushed this one to the side because we started seeing some other things work, kind of like this framework, which is very similar to what we've seen in the past. It is the copper based, but instead of using what was called alpha methylbenzylamine, we're now using what's called phenethylamine. So we extended the carbon distance between the aromatic molecule and the NH2. And what happens? One carbon bond difference. We went from an ABA layer to now a AB. Because now this becomes our repeating pattern. Layer, interlayer, layer, interlayer. So that's an AB pattern. So one carbon-carbon bond difference. We generated a completely different framework, right? And as you can see, our phenethylamine molecule right inside of the interlayer. We actually have a lot of crystals that we are generating currently with this framework that is going to be submitted more than likely either today or tomorrow, depending on if I can get all my time coordinated correctly. But yeah, these will be sent shortly, and hopefully we will have some new guest inclusion into our into this new framework. right? We also have the ability to generate pillared frameworks. We were going to save this one for working on in the summertime when we have a little bit more time. But again, copper-based. Now to generate a pillared framework, right? So instead of what we have used in the past was just a single molecule that had just one NH2, now we have one molecule that has two NH2s into the peripheral of the molecule, so that now we can kind of tether our two frameworks with one molecule. And so you can see with my crystal structure, this is something I've done in the past. It works really, really well. Just again, it just takes time for these species to really to crystallize to give us something good. Now, one of our last ones is those possibilities of that three-dimensional frameworks. Okay, and this is the biggest reason why we weren't able to complete the 3D project just yet, because upon making and synthesizing what we wanted, hopefully to develop our three-dimensional framework, we had to try the mixed metal approach. So we had to incorporate two metals. But when we did that, the metal species that was going to be in between our layers into the interlayer region. So instead of forming a diamine that we were hoping, so to mimic similar to the copper PDCA that we've been showing throughout our talk. Well, this one is from a 4-amino-picolinic acid, or at least 4-amino pyridine monocarboxylic acid, to put it simpler. Okay, but what happened was, instead of generating the metal complex with just two of the pyridine molecules, for some god-awful reason, this guy decided to take three. And it generated more of what's called a paddle wheel type structure. Well, which is good, but not for what we were looking for. So now this one would have the ability to really look into making and forming three-dimensional frameworks, but right now we cannot break, we can't break this molecule into forming some sort of hydrogen bonded species. Okay, so at this point, the amine molecules or the amine groups are, I don't have the best words for it. We just can't do the chemistry that we have been in the past with this molecule. So I've looked up some research ideas of what we're going to try over the summertime. I bought these wonderful little hydrothermal autoclaves to do some hydrothermal synthesis, and still to no avail. But I have one crystal structure that's still waiting in College Station with the hydrothermal reactors. So I guess we'll find out shortly if it actually will work or not at this point. So we're still waiting on the three-dimensional analyses. So like I said, that just puts us at a roadblock with the 3D at this point. But two-dimensional frameworks have been wonderful. The reliability, the successful guest inclusion has just been phenomenal, that we have been able to incorporate a variety of types of molecules, from alcohols to pyridines, so that we've done even some aromatic alcohol molecules like a benzyl alcohol, just not shown here. So we've seen the ability of a coordinative and non-coordinative inclusion, which again allows for so much different chemistry to occur. All right, so future plans, these are kind of some that we've already been talking about that we actually started, because this was a talk that I gave earlier this semester, so it was future back in January, but we were living some of it in the past couple months. So we want to make and create other frameworks, so the mixed amine, mixed metals, and the pillared structures. Okay, and lastly, nope, wrong one. Still wrong one. Zut alors. Touchscreen, okay, touchscreen on screen. That works. All right, so special thanks. These are all the guys that did all the work in the past with the majority of our papers. And I see there's Charles's picture that he's doing the reaction, what I was telling you about. That was really cool. That he formed the, yeah, you were working with the cobalt, I'm sorry, copper.
No,
So-
I thought it was nickel.
No, it's too blue to be nickel. So, because I know Guy in the middle is working with the cobalt species. So as you can see how it's starting to kind of go into solution. And so this is Gavin and Hone from our two papers, and Mr. David that made him a nice, wonderful shirt. So, and if anybody has any questions, I'll be happy to answer anything that you may have. Okay.
Okay, now I get it. Okay. Give me a second.
Yeah, that was an okay for me from laboratory. So, and I'm looking in Zoom. If anybody's got any questions, feel free. If not, I'm here all day, a little bit tomorrow. It's okay, Charles. You got plenty of questions because guys are already waiting for us in the lab, so.
Okay, then. I guess I can do it next time.
Oh. Yeah, I think he did it.
Good, 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 good. Does anybody have any questions? I want to thank Dr. Hogan for presenting today. Dr. Nakashian had to run to a meeting. This is recorded and is on our YouTube channel. The next honors event will be the Red River Students Project Honors Symposium, which will be held a week from Friday in Eagle Hall. We hope to have honors students in attendance as we have several who are presenting their projects. Thank you for coming. Thank you, Dr. Hogan.
Thank you.
We appreciate you being here with us today. It's very interesting research.
Well, I greatly appreciate it. It's always a pleasure.
I never know how to do this. How do you get my mouse back down there?
I know, you want to stop sharing?
Yeah,
I know it's still touchscreen, so I use that
I
to my
got you.
advantage.
recording. I'll stop recording.
That's